Great. Hi, everybody. So welcome to the Colloquium. Remember, there's 2 colloquia this week. Today's speaker is David Brooks. Travis Metcalf will be talking tomorrow at the same time. So David Brooks, he did his undergraduate degree in astronomy and maths at Glasgow University in Scotland. Then he obtained his PhD in solar astrophysics under the supervision of Professor Hugh Summers at the University of Strathclyde in Glasgow, and Dr. Jim Lang of the Soho CDS group at Rutherford Appleton Laboratory. And following a short postdoc with them, he then held fellowships at the University of Porto in Portugal and Kyoto University in Japan. And that was before joining the Naval Research Lab in 2005 to work on the Hinode Ice Project. And he has been based in Japan at the Hinode Operations Center since the Hinode launch in 2006. So with that, you can give your talk.
Thanks very much. Okay, I'm very pleased to be here at HAO for the first time and appreciate the opportunity to give this colloquium. I'd like to thank Scott McIntosh and Paul Bryans for the invitation and for travel support for this visit. Scott and I went to the same undergraduate university in Glasgow, but at different times, and Paul and I had the same PhD supervisor, but again at different times. And all 3 of us have gone around the world and finally met here, so it's quite fun to finally work with them in Colorado, of all places, instead of Glasgow. I'm going to talk today about active region outflows as a source of the solar wind, and this is work I've been doing with Harry Warren and Ignacio Ugarte-Ura at NRL mostly. I've got some papers I've written with them that I'll talk about mostly today, and I'll also show some work from related papers with a number of other co-authors, and there are too many to list here. But basically, I've been working with people at MSSL like Len Culhane and Louise Hara and Deb Baker, and also others around the world, Pascal Demoulin and Christina Mandrini and Lydia Van Driel, and a lot of other people I've forgotten. But I'll give some references to those papers at the end. Okay, so the scientific motivation behind all of this is very general. We want to understand how the solar wind is generated, how the heliosphere is generated, how it controls space weather, propagation of CMEs, the interaction with the Earth's environment. And one way to do that, of course, is to compare the observations we have with numerical simulations, but the simulations are always very sensitive to the boundary conditions in the source regions. So before we get to any of that, we have to measure the physical properties in the solar wind source regions. And I'm talking mainly about the slow wind today. And the problem we have there, of course, is that we don't yet have a consensus as to what the sources of the slow solar wind are. So how are we expected to measure the properties? And we can have a debate about that, but the main thing I'm introducing today is a recent suggestion that came out of the Hinode observations. That's what I've been working on. And that is these high temperature active region outflows that you see at the edges of active regions. And Taro Sarkao at ISAS noticed these in Hinode XRT images. This is a movie I'm showing of AIA 171 with the magnetic field overlaid in blue and red, and HMI AIA 94 Angstrom's high temperature emission. I'm just showing this to point out that, of course, many people have already talked about. It's to remind me, really, to say that the active regions and the equatorial regions have long been considered as a possible source of the slow solar wind. We've got papers from Paulette Lawyer and others talking about wind associated with equatorial active regions at solar maximum. Carol Shriver and others talking about them being sources of heliospheric magnetic fields. And when people have worked in a field a long time on specific subjects, then sometimes when a new idea comes in, there's a bit of resistance. And in the solar wind community, there is a little bit of resistance to this idea of active region outflows being a source. And I wanted to just make the point today that just because we've only started to talk about them now, doesn't mean they didn't exist before. And if we go back to before many of these studies, you can actually see these outflows in spectra recorded by, for example, SOHO CDS. And this is a map that was made, a paper by Bill Thompson and Paul Brecky using CDS back in 1998. It's a full sun map in magnesium-10, which is formed around 1 million degrees. And they've made this Doppler map. Now, the resolution is very low, but it's showing upflows in black and downflows in white. And you see this active region in the south. You have these very large patches of black upflowing material from the edges. And they didn't discuss these. They were focused mostly on, at that time, interest in the redshifts in the center of the active region core. So although the outflows were seen, they weren't really discussed as a source of a solar wind, but they were there. And if we'd noticed that back then, we'd have had 10 more years to convince people. But it becomes easier, of course, when you see them in images. And with Hinode XRT, actually, you don't see them very well in this contrast, do you? The outflows are in this region here. I don't know if we can put the light down. Yeah. Otherwise, we won't discover them. Yeah, this highlights another thing. They're in the faintest regions of the active region. You get large non-thermal widths in this region, but the intensity is low. Yeah, no. Okay, maybe I'll make a difference maybe next time, but there are propagating features here. I'm sure people have seen these in other presentations. There's been arguments about whether there are waves or flows coming out and propagating disturbances along fan-like structures here in the dimmest regions. And anyway, Sakao-san noticed these in XRT data. And I was going to say, well, these are apparent motions in the images, and we need to confirm whether they're really actually Doppler-shifted upflows. And on Hinode, we have the EUV imaging spectrometer, so we can actually look at the spectra and see if we see blue shifts or not. This is an example of the kind of scans that ICE makes. We have this is a SOHO EIT movie of a region that was observed in December 2007. And ICE is making these large field of view scans. They're about 450 by 400 arc-second field of view rasters with a 1 arc-second slit. It takes several hours for ICE to scan across here very slowly, but we can make these maps once or twice a day, and this is basically one on the 10th of December, 11th, 12th, 13th, 14th, tracking this active region from limb to limb, and this is an iron 12195 Einstrom line, which is the strongest line in the ICE spectrum. And from that, we can get Doppler velocity maps, and you can see very clearly these large blue shifts at the edges of this active region. So basically, the ICE spectroscopy confirmed that the apparent motions that you see in the XRT movies are real upflows with velocities of the order 50 kilometers per second or so, or even higher. And going back to the Sakao-san's paper, he also looked at how the locations of these outflows compared to the open magnetic field and potential field extrapolations. So the blue field here is, of course, closed and the yellow is open. And you can see at the edge of the active regions where we almost saw the outflows in the movie is located with strong open field. So that led to the suggestion that these outflows could lie on open field that connects to the heliosphere and contributes to the slow solar wind. So that's kind of a background about what people have been doing with the first results from Hinode. But moving on to my own work with Harry and others, we were looking at these and we were thinking, well, most of these measurements are kind of showing indirect evidence. We have apparent motions and upflows, but they might be under a closed field, or we have open field models with potential field extrapolation, so it may not be as complex as the real field. So is there any other way we can think of that we can try to show a more direct connection between the outflows and what you see in the solar wind? And one of the things we can do with ice is measure the chemical composition, the elemental abundances. And you can, of course, you can measure them in situ as well with, for example, ACE Observatory will use particle counting techniques to measure the ratio of iron to oxygen or something. And so we can measure it in the outflow with remote spectroscopic observations and then compare them to what you see at ACE a few days later. And that's what we've been working on. And that takes advantage of the first ionization potential effect. So I'll just give a few slides on that for people who are perhaps not aware of the details of the sort of methodology we use. The main point, I think, to say is that in the solar atmosphere, the composition is not constant. I think we all agree that whether you think that the mass supplied to the corona comes from the chromosphere from chromospheric evaporation in response to nanoflares, or if you think it's directly injected from chromospheric jets or spicules, everybody's agreeing that it's coming from the lower layers, but the composition in the lower layers and in the corona is different, and it seems to vary with the first ionization potential. So I'm just showing here a plot from Vernazza of the temperature distribution with height and the density distribution with height in the atmosphere. And something is going on in the chromosphere here. When you have elements that have a high first ionization potential, they're difficult to ionize, and they end up producing a photospheric abundances in the corona and in the fast solar wind. And you can see that in this plot here. It's a wind speed velocity with time, and on this axis I have a ratio of magnesium to oxygen abundance, which is a measure of the degree of enhancement of the composition in the wind. The ratio of the coronal composition to the photospheric composition. So when the wind speed is high, the ratio goes down low and is close to photospheric. But when you have elements that are already ionized in the chromosphere, then they are preferentially enhanced in the corona and the solar wind. And you see here when the solar wind speed goes down, the composition goes up. And that makes this effect a good tracer of mass flow into the corona from below. And with ice, we have quite a few diagnostics that can look at this. I have a plot here of the first ionization potential against the ratio of coronal to photospheric abundance. And I'm just showing the elements here so you can understand what elements I'm talking about. If we take ratios of, for example, argon as a high FIP element to calcium, then that becomes useful for high temperature events such as flares. We have silicon and sulfur ratios that are good for active regions and quiet sun. And there are oxygen, magnesium, silicon lines in the transition region that are useful for looking at the abundances in transition region impulsive events. So with ice, I've said here we've opened a new era in elemental abundance studies. Maybe that's a bit strong. Renewed interest in abundance studies has come about because of ice. Now, we don't know exactly what causes the FIP effect. There's a promising model from Martin Lamming that is based on the forces acting on Alfvén waves, but even that is still a static treatment, and we probably need time-dependent simulations to fully understand the FIP effect. But even if we don't understand what happens, we can exploit as a diagnostic to see if we can learn something about these outflows. The difference is large. There's a factor of 3 to 4 variation. So it's a big effect. And compared to the diagnostics we have, it's very noticeable. Just to give you a little bit of technical detail on the actual ice method, so you can see the type of assumptions we're making in this. I'll move on to show you one of the diagnostics. This is the silicon-sulfur ratio that I mentioned. First of all, I have here the theoretical emissivity for sulfur 10. This is temperature and density. And the sulfur 10 emissivity and the silicon 10 emissivity are very, very similar. When I flick between these, you'll see it'll change a little. But in temperature space, it's very, very close. That's it changed. There's a slight variation in density, but going between them, they're not much different. And when you look at the ratio, you see in the region where the line is formed between about log temperature 5.7 to 6.2, or density 7 to 10. Where it's sort of yellow here and going to blue, it's the variation is not very strong. There's about 30% variation in this region. At high temperatures, there's a huge deviation across this steep gradient here, but we can attempt to remove that by by calculating the temperature structure across this full temperature range using all of these lines from ice, from silicon 7 up to iron 17. When we fold that into the emissivity, then that variation is removed. But most of the active region outflows that we're looking at actually fall in this region where the ratio is very flat anyway. And I'll show an example of that in a minute. So just a summary of that algorithm. What we'll do is we measure the density using the iron 13 ratio, and then we calculate the DEM using all of the low FIP lines from the low FIP elements, iron and silicon. And when we do that, because they're enhanced, there's a factor of 3 difference. So when we calculate the sulfur intensities, they will be a factor of 3 or 4 much higher than observed. And that's the measure of I'm calling the FIP bias here, the degree of enhancement of the coronal abundances. And typically for these outflows, if you just look at the density, we'll put a density against the ratio here, plot it on the graph, it will come out around log density of 8.5. And the typical DEM, which are an emission measure, these curves are emission measure loci curves. So this is using the theoretical emissivity. If there's no intensity, then this will be the limit, and the emission measure must fall below this. And we have a Monte Carlo simulation of the emission measure here. And the dashed lines are the Monte Carlo simulations. And red is not coming out on this, I think. There's a red line here, which shows the... Can you actually see red on this projector? No. Yeah, on that previous plot there was red as well. So red's not coming. There is a red line going through here as the best fit. And it's typical of the outflows to be peaked in a temperature of 1 to 2 million degrees, and it falls off very steeply as you go to lower temperatures. It's maybe 2 orders of magnitude higher at the peak than it is in the higher transition region. So they're very much coronal. We tested this method on coronal holes because we expect them, polar coronal holes are expected to be the source of the fast solar wind. So we should get photospheric abundances if everything is working correctly. So this is a polar coronal observation from ice, another scan across this region. Just went in and take some boxes here and calculate go through the whole methodology, and we come out with an abundance of about 1, which is consistent with what you expect in the fast wind. So the method seemed to be working okay. There's a caveat here about sulfur, which is under the kind of dividing line between low and high FIP elements. So it doesn't always behave completely like it should as a high FIP element. But for active regions, there's some evidence that the evidence suggests that it is behaving like a completely high FIP element in active regions. And in fact, recently in the solar wind in situ data, people have started to detect a more gradual change from the low FIP to high FIP elements. So if you take, for example, 2 high first ionization potential elements like neon and oxygen, then oxygen will behave like a low FIP one compared to neon. So even though they're from the same category, there's a variation in how they're behaving. So we found this one to work quite well for these studies. And I'll move on to the actual results for the outflows then. Going back to this December region I mentioned before, we had these scans every day as the region crossed the disk. These are the Doppler velocity maps. When the region is coming round from the solar east limb, you see a very large outflow on the western side directed towards us. Then when it reaches the central meridian, you start to see outflows on both sides. And then when it rotates away, we see it on the east side. So we can go into these regions, and I've put little boxes in amongst these, and looks something like this. This is a plot of the in situ measurements from ACE solar wind ion composition spectrometer through the solar wind speed. And the outflows are falling in this shaded region here. And the results are in this range, kind of 2.5 to 4, an average of 3.4, which is typically what you expect in the slow solar wind. And you can see an overlap with some of these values here. So basically the ice abundance measurements are confirming that the composition of the outflows is the same as you get in the slow solar wind. This is red as well, by the way. I'll point that out from now on when the red ones come up. Okay, so actually recently this data has all been recalibrated, and the ice data has, the atomic data for these diagnostics has been updated as well. So this figure is slightly changed, but basically the conclusions are the same. Line profiles, the blue wing, indicative of high-speed upflows. You can see here, this is iron 8 going up to iron 16, and these sorts of asymmetries have been seen by many people. Hiro Hara found them associated with the foot points of some loops in active regions. Bart DuPonte and Scott have looked at them in relation to spatial correlation with spicules and jets and so on. But they're seen much more strongly in the outflows, and they're seen much more strongly. This is the iron 8 line. You can see it's just a fairly small upflow component, but if we go up to iron 15, then you have a big hump here that I've just shown, which were all done with a single Gaussian profile fitting. So after we completed that, we moved on to this to say, okay, does it make any difference if we look at the composition in this component compared to the bulk outflow? We have this slightly blue shifted component and then a high speed component. So I did the same analysis for this region for the high speed component. So here I have again an intensity map, and here is the Doppler blue and no redshift map. The black lines are the contours that show the locations where the asymmetries are larger than about 10%. So there are other asymmetries in this region, but these are the strongest ones. And you can see that the contour falls right around this big blue shifted upflow, and in some blue shifted lanes between these bright fan loop structures that you get on the other side. And again, I've gone in with little boxes to measure the composition here. First of all, measuring the density and calculating the DEM again. And for the bulk outflow itself and the blue wing, the results are fairly similar. The DEM looks fairly similar. It's obviously weaker emission, so the emission measure is about an order of magnitude down in the blue wing. But they both seem to be dominated by coronal emission, and the composition is about, in fact, the fit bias is about 3, which is again what you expect. So both of these are flowing out with a similar composition. And one of the interesting things about this, to me at least, is that this suggests that the asymmetric component is coming from coronal plasma. So there's some, how to put this, a clue there about how this fits in with, for example, spicule explanation. In, for example, Martin Lamming's model, if you have material rapidly passing through the chromospheric region where the fractionation happens, then you shouldn't get a FIP effect. So if that's happening, then how does it produce this coronal plasma? Is the model missing something, or is this more indicative of waves coming out on open field? There's something, there's maybe a clue here to bring the observations and simulations together, but yeah.
Martin's model requires that the alpha wave bounce around for a hell of a long time.
Yeah.
From observations of alpha wave.
You don't see that. So when you have the spicule going, you're expecting it to launch a wave?
Actually,
No, oh, well,
but there probably is some shock associated with the type 2 spectrum. But there's a lot of heating intrinsic to the spectrum itself. That plasma is being heated in the thing itself. So, I've always looked at it as a two-stage process. Right, you heat it and then you either accelerate or take it more, depending on whether you're open or closed field. And the waves are there all the time because all of the magnetoconvective stirring, both in the torsional, is being transferred into those structures and roaring up into the corona. Everywhere, you see it everywhere.
yeah.
And so the idea always was, I think, that the process that's loading mass and the process that's driving the waves are kind of similar but disconnected.
Okay.
And one is pushing mass into the system, and the other is helping to equilibrate it and keep it hot, if you like. Whereas in a coronal hole, you get exactly the same process. It's in an open field line, and the material now is heated initially, accelerated initially, but then given a push by the wave pressure behind it. So it's kind of like two sides of the same coin, right? In a trap field, those waves are doing their turbulent best to cause results. But in the open field, the wave energy, instead of heating being dissipated in the corona to keep the plasma at a few million degrees, is now accelerating the plasma instead. So, but I think there's a fairly substantial amount of heat being deposited in that blob of material.
And this is in open field region, of course, but it's opened up in the outflow. So yeah, we can talk about that. Well, I'd like to talk about that afterwards because I'm wondering how that will produce the. Normally we expect it to be confined, and then the FIP effect will happen.
Well, I think the old case papers were the amount of FIP bias was to do with the time history of the plasma, right?
Well, yeah, if it's already enhanced and then it's released, then that's okay. Yeah.
So we thought about it a little bit.
Yeah. Okay, let me move on, and we can come back to discuss that later. The results for these high-speed components are basically almost the same. Slightly tendency to be slightly higher, but the average comes out about 3.4. So yeah, they're basically, whether you look at the whole emission as integrated together, or the bulk outflow and the upflow, the high-speed upflow, it comes up with the same composition. And another interesting thing about this region is that when you then go and look at the ACE data several days later, it almost matches up. So obviously when we have the outflow from the active region, it takes several days to get to the near-Earth environment. And it can then be measured by ACE SWICs. And here I have these orange points are measurements of the average of the outflow on the western side. And that outflow, when you saw that it had come to the central meridian and it was almost directed at the Earth. So we averaged up the measurements there. And the blue points here are the daily averages that are measured by ACE, time shifted several days later, once the plasmas had time to reach the Earth. And you can see here it's almost a match. It's almost like the results converge. And then if this is the outflow coming towards you, it points at the Earth and the results converge. And then when it moves away, they've diverged again here. They've gone off in different directions. So that was quite interesting. I mean, it's obviously a very uncertain comparison, but it's quite interesting that you can apparently perhaps see a signature with ACE. So what do people think about these outflows? Well, a lot of people have been studying them as possibly interchange reconnection, where the closed field loops, as we've just been discussing there, you have the loop confining the plasma and the abundance becomes enhanced, and then it reconnects with open field, and the composition that's already been enhanced is then released. And Deb Baker and Lydia Van Driel have done a study of this. They looked at another active region which shows outflows in this dark area. You see the strong blue shift here. And there are open field lines here, and then this is a nonlinear force-free field extrapolation. So you have the closed field loops and the open field here. And they looked at quasi-separatrix layers where the connectivity is very different. It goes off in different directions. And these are unfortunately the red lines here, but they're projected the positions of the QSLs down onto the plane of the corona, and they do actually go through this outflow region. So that's one idea behind that. And if this process happens, then when you have the reconnection, you might expect to see some signature of that. And Giulio Delzana has written a paper where he looked at radio data from Nobuyama radioheliograph, and he did see some weak noise storms at the edges of one of the active regions he looked at, which would be consistent with this picture. So at this point, we have a scenario where you have plasma confined so that the FIP effect takes place, the abundance becomes enhanced, then you have reconnection that opens the field, that enhanced abundance comes out. You see it as propagating apparent motions in XRT movies. You see it as blue shifted upflows in ice. The abundance measured is the same as the solar wind. It comes out on open field, travels to ACE. You measure the composition there and it matches. So there's a body of evidence building up that they're contributing to the solar wind. So you'd be forgiven for asking what's the problem here. But there are a couple of issues. And one of them is that when you look at these outflows, the mass flux that comes from these small regions is generally too small. If you look at what you see with ACE, you get 15, 20% of the mass flux when you've got one active region sitting there on disk. So that suggests that there must be other sources around on the sun as well. It's not all coming from the active region, which we expect anyway because you don't have active regions all the time. Perhaps a bigger problem is that for this region I've just been discussing, the December 2007 region, it's completely covered by this helmet streamer. You see the active region underneath here. So how can it even get out of here? If there may be open field under here, but then it's completely encompassed here. And that turns out to be quite a common problem. Sarah Edwards at St Andrews has been working on this, and she looked at 7 regions. Again, these are ice Doppler maps. You find the outflow regions here in blue, and she's done a nonlinear force-free field extrapolation, and the yellow lines are open fields, so the yellow lines of open field are coming from the blue outflow regions. And then what she did was she made a map of how high these field lines go. So where it's light blue here, it means the field is closed very low down at heights maybe only 10% of the solar radius above the surface. But where it's gone black here, it's extended all the way up to the source surface of the model, which is placed at 2 solar radii. So these are very high reaching field lines. So in this case, the plasma on the open field can escape all the way up there. But that turns out to be quite an unusual case. Most of the regions she looked at, well, she's looked at 7, and the other 6 of them are more like this. Again, you find the outflow, as usual, do the extrapolation, but maybe in this case there's no open field at all. And when she looked at this map of how high the field lines are reaching, then they're all closing down very, very low. So there's no high reaching field, there's no open field, and there's no obvious way for it to escape, for the plasma to escape. On the other hand, again, you do see indications at ACE that something has got there. The important plot to look at is this one. It's iron over oxygen ratio, and that's a proxy for the fit bias, again, the amount of enhanced composition. And when the active region comes round near disk center, you see the fit bias jumps up by a factor of 3 or 4 as if active region plasma has got there. So even if it's not in the outflow, people would previously say the slow solar wind has the composition of active region plasma, and that's what you see here. The active region appears and up it goes. So it seems like it must be getting out somehow. So Len Culhane and Christina Mangini and me and others have worked on a paper. This is really their paper, but they came up with a complicated two-step reconnection process to get this plasma out. So first of all, you have reconnection between the closed field of the active region and the large-scale network loops. Then the plasma can move along these loops to a higher latitude. This is a tilted map, so it's not a polar latitude. It's just higher equatorial latitude. In her simulation, Christina's simulation, there's a null point here where you can have reconnection for the plasma to escape. So if you can channel it along these long loops, then it can escape up here. And again, if that happens, you might see some signature of reconnection in this region. And they did what Giulio did. They looked at radio data and these crosses here where they found some weak radio noise storms suggestive of that. And they're arguing that the plasma can escape even when it seems unlikely. But we were wondering if that kind of complex process is really necessary in general. Obviously, you have other sources on the sun. This is that December region. You can, I don't know what to say about this. It's red, of course. So the dark parts of the red are coronal holes. And there's another active region here. So there are other sources that the problem we have is that with ice, this spectrometer's field of view is very small. So it's difficult to go and check for other sources. If we're doing an observing campaign, then everybody's going to point at this big active region. Nobody's going to go off and check the equatorial coronal holes. So what we did to come up with a solution around this is make a full sun scan with ice. So we did this in January 2013. These are the usual raster scan sizes. They take an hour or two to scan this region. So over a period of 2 days, we can build up an image of the full sun. It's obviously not simultaneous, but we do have all of the diagnostic lines, density diagnostics and everything. So we can do the entire analysis that I just did for the outflows over the whole sun. And that's what we tried to do. And these are some of the ice full sun images. So this is iron 8 going up to iron 16. These are, again, they're not simultaneous images. They can't compete with AIA for time cadence, but they are pure temperature images. And we can get Doppler maps from them at all these temperatures. So we can make a map of where we see these upflows. And we can also, rather than go in and measure the composition in a small box, we just measure it everywhere and make a map of the composition over the whole sun. Also, I worked with Mark DeRosa. To modify PFSS to work for the ice data. So these are potential field extrapolations across the ice. And from that, we can get a map of the open field locations. And combining them all together, we take the map of the upflow and the map of the composition and the map of the open field, and we make what we're calling a solar wind source map. So it's ticking the 3 boxes of the 3 ingredients. It's showing regions of upflow on open field with the slow wind composition. So here's an example of the Doppler map for the full sun. This is for iron 13 202 Angstrom line. And we use this to identify locations of the upflows in blue Some of these upflows may be within closed field, as I've already said. So we overlay the open field map and we can determine which ones are on, or which upflows are actually outflows and not just upflows within closed field. So these, the green lines here are showing the open field regions, and the orange ones here are showing the closed field regions. So you see, for example, this strong upflow area has open field extending out of it, but there are other blue shifted regions in here that are below closed field, so you don't see anything there. And then we can look at the composition map. This is an example of that. It's showing the degree of enhancement, so the darker areas around here and here have a photospheric abundance, and then the brighter or dark, well, they become dark green in this color scheme now, showing the regions where the composition is enhanced. And you can see again, this is around the area where we saw the upflow on open field, so it looks like there's an enhanced composition there. And what I did just to represent them so you can see the locations compared to features on the sun was take the AIA data that we used to co-align the mosaic and overlay the source regions that tick each of these boxes on top of that. And that's this next map here. So this is an AIA composite image showing all the different regions. These areas which have now come out as green are showing the locations of upflow on open field with solar wind composition. So at the edge of this active region, you see a source here, and in this active region on either side, again, you see these outflows. And around this active region, there's some equatorial coronal holes here, where you see some source here. So there's a contribution coming from that as well. So we decided to look at what is the relative contribution from the outflows and from other sources in this map. And in fact, calculate the mass flux, because that was one of the things that seemed to be too low if you just look at the active regions on their own. And we have, of course, we have the density and the velocity at every pixel in this map, and we know the area of all of the source locations, so we can calculate the mass flux from that, which is what we've done. And by projecting that to the ACE position, you can convert it into the proton flux density that ACE measures. These are the ACE measurements here. This is a few days after the full sun map, 4 days later. And the average of the ACE measurements is the top line here. This is from the solar wind electron proton monitor. And these two lower lines are showing the limits from the calculations from ICE. There are two measurements there because we have difficulty in determining the rest wavelength of the velocities with ICE. We don't have an absolute wavelength calibration, so we have to make an assumption about what the reference wavelength is and calculate a relative velocity. So we've got kind of two extremes. We can say the error in the velocity measurement is about 4.5 kilometers per second. So if we only include pixels that have velocities that are larger than that, then that'll be a lower limit, because there'll be some that have 2 or 3 kilometers per second that are actually blue shifted, but it's too low against the error. On the other hand, we know that from work by people like Hardy Peter and so on, that the corona possibly shows a slight blue shift. If you look at like iron 12, the rest wavelength may be slightly blue shifted by 1 or 2 kilometers per second. So if we choose that as the rest wavelength and then include everything, that will be the other extreme. It will be too high, because some of those velocities are probably a velocity of 1 kilometer per second. That might actually be a red shift of 1 kilometer per second. So we've got the two extremes there, which is why you have the two lines. Well then, okay. Well, I mean, it's highly plausible. So in this map, so we've got a lot of constraints, and we still come up with enough mass flux. So if you relax all of those constraints, you're obviously let's say, okay, it seems more intuitive to say it's got to be on open field than closed. It seems more intuitive to say the abundance has got to be correct than wrong. You know what I mean? Okay, yeah, I don't know the exact number, but I can easily check that and tell you tomorrow, probably. We've got all the data upstairs we're working on, so. Yeah, yeah, no, I haven't actually, I can say I haven't thought about that at all yet, but now you've asked, I'll think about it. Asymmetry of silicon-7. Asymmetry of silicon-7.
Doppler shift in the closed loops is correct, but the asymmetric component is still sitting at 100.
Mm-hmm. Yeah.
The only way you get the red shift is because you get a cycle. There's a mixture of open and closed loop on monstrous line scale. Yeah, I guess it's also consistent.
When you look at you've probably seen Harry and others, you look at the fan loops on the edge of the active region, you see it transitioning from the blue shifted outflow down through temperature.
But the thing is that asymmetric component.
Well, I mean, in the outflow, like I showed earlier, I mean, it will change with temperature, the asymmetric component. It tends to be much smaller in silicon-7 than, for example, iron-15. And that brings up another thought, because back to the mass flux thing, that is all calculated with iron-12, so you'll get a different answer if you use another line, because the velocity structure is different. You know, the velocity map will be different in silicon-7. No. Well, when the active regions go away, the streamers and everything come down, don't they? I'm not actually sure about that. Yeah, I mean, this is it's a solar cycle thing. So it's something else. But on the other hand, if you make a map like this, you should see them, yeah? Whatever it is. Not necessarily. Well, I mean, you see open field outflows with coronal composition away from the active region as well. It's just that they're not dominating at this time. But I don't know what would dominate at solar minimum if you did a similar map. Maybe it would be the case that it's all coming from higher up in streamers and stuff like that. You know, I guess we're arguing that the outflows are dominant in this observation at solar maximum, but that doesn't necessarily make it true in the rest of the solar cycle. It's obviously coming from a number of sources, right? So it's more a question of which one's dominating. We've got activation outflows here. There are coronal holes. If you take this mass flux calculation, then there's a missing mass that might be coming from higher in the atmosphere that you'd see with UVCS, like in streamer blobs and stuff like that. What is the relative contribution? And in this observation, it seems that the outflows have the largest contribution. But if you go to a different time or a different phase of the solar cycle, then that won't be true. I mean, it's obviously not true at minimum because there's no active regions. But it must change with time. Yeah? Does that answer? Maybe? And if you see redshifts in Silicon-7, you won't see them on this projector.
So they were there all along.
Yeah.
They just happened last week. It makes you feel any better.
Well, it'll be okay on the video, I should because they'll see the slides.
Right, yeah. They will, hopefully.
Yeah.
Right, thank you very much again.
Thanks.